So I'm going to talk about scalar conservation laws with discontinuous flux function. And it's a joint work with Boris Andrianov, which is professor in Besançon, and Nicolas Seguin, which is a colleague of mine in Paris. This problem has been widely studied during the last 15 years because it arises in several real-life applications. And I will mention one, but I will detail one, but I will mention several. And let's detail the outline of the talk. At the beginning, I will present a theory for scalar conservation laws with discontinuous flux. And this theory is mainly due to let's mention the contributions of Kenneth Carlsen, John Towers, Adi Murti, and also Boris Andrianov a lot, that allow to have a generic framework so that one can study real-life application problems, and that will be the second point. So I will apply this theory to the case of porous media flows in heterogeneous rocks, and where this kind of problem appears in a very natural way. And then, to conclude, I will talk about a track to derive error estimates for the Godunov scheme of the problem. And there is still some open questions on that point, but I will present some, in particular, in one case, there is a complete study. And first, I recall some basic stuff on the scalar conservation law there, which is it's an hyperbolic scalar conservation law. S, which is the unknown, is the scalar quantity, so it's not a system. But this subject has been widely studied since a long time. In particular, let's mention the contributions of Oleinik and Volpert and Krushkov in the 60s and 70s. And one first remark is that even if I start with a smooth initial data, the solutions of this equation may become discontinuous after a finite time, and then dealing with strong solution, the notion of strong solution or classical solutions to this equation are not well suited. So we have to select another notion of solution, and the first idea is to go to the distributional sense, so the notion of weak solutions. And so at discontinuities, when one writes the conservation at the level of the discontinuities, one obtains the well-known Rankine-Hugoniot condition. That means that this is the speed of the discontinuities, and this is the left state and right state. So the speed of the discontinuity is given by this quantity. But this, when we look for weak solutions, the problem is that there's, in general, an infinite number of weak solutions to this problem. So strong solution, we lose existence. Weak solutions, we lose uniqueness. So one has to add another criterion. Let's say, for example, the lax condition. That means that the characteristic curve along which the solution is constant just enter the discontinuity, but it cannot leave the discontinuity. This is also the same. This is equivalent to the Oleinik condition for scalar conservation. Now, I will speak about a few words about undercompressive shocks, because in some particular physical configuration, in fact, some information can be generated by the shock, by the discontinuity. For example, in traffic flow modeling, when the size of the road is changing, there can be some wave leaving the place where the road changes, or also when you have toll gates on the road, it will be the same. there's also models for water treatment, where in the modeling of clarifier thickener units, you have also this type of problem, and in that case, because you have different spatial areas, and in that case also you have to allow the undercompressive waves. Also, when you study the Burger's equations, but you put a small particle in the flow, then the small particle will interact with the fluid, and you have to allow some undercompressive waves because of the small particles. And this interaction also generates information. And what is more interesting from my point of view, because the problem I study is related to porous media flow with heterogeneous rock type, and I will come back on this point in the second section of my talk. So, what occurs for undercompressive shocks? We still conserve mass. This is we still conserve mass, so we keep the Rankine-Hugoniot condition. But now we relax the lax condition. It means that now the characteristic curves can leave the discontinuity. So we have some waves leaving the discontinuity. So in what follows, I will just assume that this is the case in many problems, that the discontinuity does not move. Like, for example, rock heterogeneity, or also in traffic flow modeling, the change of the road type or the toll gate, it does not move. And we consider the typical case where, we consider this kind of problem. So the scalar conservation law, but now the flux depends on x, but in a discontinuous way. On the left, if x is negative, you have one flux function, which is bell-shaped. It means that it's increasing then decreasing. And on the right, you have another flux function with the same shape, but it's not the same flux function. And we also assume that they are compatible, so they connect. They have the same value here, and they have the same value here. This can be slightly relaxed. But okay, this is the assumption of the problem, and this is really natural in the porous media context, and also in the traffic flow context. Okay. What do we expect from the solution? We expect that, okay, in the left and in the right, we want to have a usual entropy solution. So this can be written, we use the Khrushchev formalism for this. And okay, we compare with whatever the kappa, which is a constant value, a real value in 0, 1, we ask this inequality to be true for test functions that vanish on the interface at x equal to 0. And what is this? S minus kappa is the entropy, and phi r s kappa is the entropy flux function corresponding to the function FLR. The FLR, when I use the double subscript, it means either FL or FR. So I have one side, in each side, I have usual entropy solutions. And this is sufficient, thanks to the result of Panov, to claim that, okay, if the solution is bounded, and it's true here because of the compatibility condition, the solution remains between 0 and 1. And if the solution is bounded, this type of inequalities is sufficient to claim the existence of strong traces on the interface. So my solution, even my solution a priori lives only in L infinity, which is it is bounded, but because of this family of inequalities, it admits traces on the interface, and I will be able to speak on the left trace and the right trace. That way, I will denote them by SL for the left trace and SR for the right trace. And then, now the Rankine-Hugoniot condition with 0 speed is nothing but I want the flux to be continuous. So this is the Rankine-Hugoniot. Okay. Now, as it was the case for the case of usual scalar conservation law, enforcing the Rankine-Hugoniot condition is not sufficient to have a unique solution. So I will speak now about undercompressive and overcompressive shocks to be able to define properly the thing. Okay, so what is an undercompressive shock? It's a steady shock. It means I have to fulfill the Rankine-Hugoniot condition. So the value FL of SL has to be equal to FR of SR. So the value are equal. I'm on the same horizontal line. And the derivative on the left is non-positive, is negative even, and the derivative on the right is positive. So the wave on the right goes from the interface to the right, and the wave on the left goes from the interface to the left. So it leaves the interface. Okay, so the other, all the couples, with a slight abuse of notation, all the couples that do not fulfill the undercompressive condition, I will call them overcompressive. It's not, okay, it has a slight abuse there, okay, it should be or there, sorry, I corrected this, but it was, I did not send the good version. Okay, so this is or. Okay, then when I plot here SR and there SR, and I plot the set U and the set O. The set U is a non-increasing curve. It's a decreasing curve there until a maximum value that is here as the maximum of SL. The S bar L is just this is the maximum, in fact. So it's there. And then the curve starts to be increasing, and then I'm in an overcompressive configuration, and all this curve here is overcompressive. So I just have a small part here that is undercompressive. Okay, so as I claimed before, there's an infinite number of solutions to the problem. And this has been pointed out first by Adi Murthy, Siddhartha Mishra, and Vera Pagauda. And then there's a very nice works of, it's not Burgers, it's Berger, that is now in conception. Burgers is unfortunately not there anymore. And also Andrianov, Carlson, and Reisbro. They classified rigorously the notion of, they gave a rigorous notion of solution, and they classified following the undercompressive shocks. Okay, so I have an infinite number of solutions, but in fact I have also an infinite number of L1 contraction semigroups. Okay, so this is solutions for which the distance between two solutions is decreasing with time. There exists a one-to-one mapping between the set of the L1 contraction semigroups S with the set of the undercompressive shocks. In fact, in each L1 contraction semigroup, there's one and only one undercompressive shock that is allowed. Okay. So in each semigroup, there's only one undercompressive shock, but in each there's only one undercompressive shock. But for all undercompressive shock, there's L1 contraction semigroup that corresponds. And with this undercompressive shock, I can define the space, the set. It is called the L1 dissipative germ, where the traces live. The one-sided traces on the interface, they live in the set where the Rankine-Hugoniot condition is satisfied, and the entropy compared to this steady undercompressive shock is decreasing at the interface. You have decrease of the entropy, but the entropy now depends, the choice of the entropy depends on the undercompressive shock you have selected. So it's called an adaptive entropy. Your entropy has to be adapted to each notion of solution. Okay, now I can also parameterize this problem via a flux constraint. Maybe I come back on the figure. So on the interface, I want the Ronchi-Lugoniot to be satisfied. So I want FL of SL to be equal to FR of SR. So the flux, the value of the flux is limited by this value there. This is what I will denote by the optimal value of the flux, F opt. It cannot be greater than that. And this is Q is the value there. Okay. So now, in the interval between Q and F opt, if I come back on the figure, on all this interval, I should have plotted F opt there, but on this interval, I can, if I choose a value, there's a unique corresponding undercompressive shock. So, I expect to a value, I can define a corresponding undercompressive shock. And also, I can also, to an undercompressive shock, I can define the value of the flux. So the one-to-one, trivial one-to-one mapping. So sometimes we write this in this way so that we stress this correspondence. And so now, if I choose a flux constraint, a flux value, F bar, then in fact the set of the traces at the interface is just the possible traces is just the undercompressive shock that is allowed by this flux constraint, and all the overcompressive shocks for which the flux is smaller than this value. So, in that case, what we obtain that at the interface, the flux cannot be greater than this value. So, in fact, this value acts like a local constraint of the flux. You have a maximal value that is non-trivial, that the flux cannot overpass this value. And among all the entropy solutions, if I choose the greatest value, I obtain the optimal entropy solution, and this solution optimizes the flux at the interface. Okay. Now we look at a particular case. My flux function do not depend on time on x anymore, but I put a flux constraint. This is just the particular case where I choose the same function FL and FR. And this has been introduced by Rinaldo Colombo and Paola Goatin to model toll gates on highways. And it has been studied by Boris Andrianov, Paola Goatin, and Nicolas Seguin from a numerical point of view. They prove the convergence of finite volume schemes for that problem. And so, let's focus now on the Riemann problem for this simple problem there. So I choose piecewise constant initial data, and what is the flux with the constraint as interface is nothing but the usual good enough flux. You compute the usual good enough flux, then you check if it's smaller than the constraint, you keep it. Otherwise, if it's greater, you constrain it. You just take the minimum between the constraint and the good enough flux. Okay, and the good enough flux is just the usual one. But now, since my function f is bell-shaped, this very complicated expression to compute there can be computed like this. I find the maximum, the point where f reaches its maximum value, and I compute this stuff, and this is, and then the constraint good enough scheme is exactly the minimum of f bar, the f of the minimum of UL and S bar, f of the maximum of S bar and UR. So this is the exact good enough solver for this problem. Okay. Now let us extend this to the case where FL and FR are different. In this case, we would like to do everything in the same way. But we have to replace the usual entropy solution by another one, which is the most natural solution to replace this one. It's the optimal entropy solution. And so the AB entropy solution, it means that A and B is an undercompressive shock that is physically relevant for the problem. It can be seen as the solution of this constraint problem with a constraint on the flux at the interface. Without constraint, the formula for computing the good enough flux is still valid, but you have to change FL and FR, and then you apply the constraint, and you just obtain the exact good enough flux for this constraint problem, and then for the computing the AB entropy solution. Now, why computing? Okay, just say one more. This will be linked to this. Okay, here I replace the usual entropy solution by the optimal entropy solution. It's very natural because it's an extension. In the case FR equal FR, these two solutions are the same. Now, in the case where FR is not equal to FR, the entropy solution, the optimal entropy solution is not in general the vanishing viscosity solution. What I will call the vanishing viscosity solution is the solution of this problem. F. I regularize this problem with an epsilon viscosity, and I take S is equal to the limit of S epsilon, and epsilon tends to 0. But this solution is not, in general, the optimal entropy solution. So now I will study the viscosity. Okay. So when you check this, you say, okay, I have to select my solution following the viscous process that is hidden behind. The entropy solution in the case of a homogeneous domain with a continuous flux function with respect to space is just defined in general in this way. But if one puts another diffusion process, you converge toward the same solution. So, in fact, the notion of entropy solution is not depending on the diffusion process that we have, and we take the limit on the diffusion process. So that we make vanish. So now we will do the same, but now the diffusion process can depend on X also, because I have physical variation following the domain, and so the diffusion process has to depend on X. So this problem, we assume that it has solutions that are bounded infinity, and that they fulfill entropy, the same type of entropy inequalities. But okay, this cannot be 0 there, otherwise you would have the entropy solution to your scalar conservation law. So here it will be something which tends to 0. which is small, it tends to 0 in the distributional sense. And assume also that the saturation converges, the S epsilon, the unknown converges towards something strongly. This can be proved. This is really technical, but this can be proved. Okay, then at the limit, you recover exactly your scalar conservation law with discontinuous flux. In each subdomain, you recover your entropy inequalities, and then you just in order to determine what is the good, the physically relevant solution to your problem, you just have to determine which undercompressive shock is allowed at the interface. There is one. Let's determine which one. Okay. Moreover, to do that, we have to assume that, okay, my problem with epsilon regularization, it satisfies also entropy Kato inequalities. It means that it's entropy inequalities, but you can compare two solutions. It's a bit strong. You do not compare only with constants. You're able to compare two solutions and across the interface. You're not allowed to compare with constants across the interface, but with solutions. This can be proved in many cases. Okay. And assume that there exists a steady state of the problem that converges toward an undercompressive shock. So S epsilon tilde converge toward your uncompressive shock. And then you pass to the limit, and you obtain that A, B is an undercompressive shock at the limit. So to pass to the limit in the problem, one has to study the viscous problem. And in particular, its steady state, to know what solution of the hyperbolic problem we have to select. And as soon as you have determined one undercompressive shock, you have the corresponding flux constraint that can be computed, and you can compute the Godunov scheme in a very cheap way. So the stuff, the main task is to study this regularized problem, and in particular its steady states. And as soon as we find this limit, we have an efficient scheme. We find a steady state that converges to an undercompressive shock. We have an efficient scheme. Okay. Now, I will apply this to the porous media context. So, okay, I consider a one-dimensional porous media flow, and the porous medium is made of two rocks. There's a left rock and the right rock. Okay, it's an infinite domain. I'm just solving, in fact, Riemann problems. My phases are immiscible and incompressible, and so they fill the pore volume. And so this is the saturation of the phase A, and this is the 1 minus the saturation of the phase B, okay? Because SA plus SB is a constant because of this assumption. I have these two constitutive equations. And moreover, the phase pressures, P, they are related by the so-called capillary pressure relation. PA minus PB it's an increasing function of the saturation of the phase A. But this function depends on the rock type. So, and they are strictly increasing, and okay, we do some assumptions on this function, but they are not restrictive at all. And one has also an important stuff is that this function vanishes when S is equal to 0. And this function there vanishes when S is equal to 1. This is okay. So, okay, when we do a small number of algebraic computations on the calculations on the problem, and then the problem reduces to this simple problem. So one single degenerate parabolic equation in each subdomain, and at the interface you have the flux continuity. This is nothing but conservation of mass, and okay, this is, you want the capillary pressure to be continuous, but it's not always possible, so you have to deal with maximal extensions, you extend your capillary pressure curve into a maximal monotone graph, and this is physical. And then you can, this condition is in fact, in some sense, the continuity of the capillary pressure. And in this problem, the flux functions are naturally bell-shaped. That's when consider gravity. Okay, so a theorem that was in my PhD was the following. So there exists a unique mild solution. Okay, the notion of solution to the problem is quite complex, but there exists a unique mild solution which is bounded between 0 and 1. For if the initial saturation is, and one has contraction properties between one has contraction, so the distance between the two solutions is a decreasing function of type in L1, the distance in L1. And this unique mild solution can be approximated thanks to a monotone finite volume scheme, and so we can compute it. Okay, and we have also to prove uniqueness. In fact, is based on such Cato's inequalities. So we have all the ingredients to take the limits of the vanishing, the so-called vanishing capillarity limit. So what is the vanishing capillarity limit? You say, okay, I'm looking for large time scale and large space scale. Let's rescale. I change x into x over epsilon and t over t by 2 over t over epsilon. And then your scalar conservation, your degenerate parabolic scalar conservation law is not changed, except that there's an epsilon there in front of the diffusion. At the interface, the flux continuity, you have an epsilon there, but the capillary pressure continuity is still there. And for epsilon fixed, of course, the problem admits a unique mild solution. Now we have to let epsilon tend to 0. So formally, when one lets epsilon tend to 0, there, this term will vanish and this term will vanish. So we just recover a scalar conservation law with discontinuous flux function. Okay, I have a weight, but this does not play any role in the following. So it's there because of physical consideration, but it can be, you can forget it. My functions are bell-shaped. Just so, following the preceding study, I also have the Rankine-Hugoniot condition at the interface, and following the theoretical study, I just have to know whether the undercompressive shock to obtain a good scheme, the good enough scheme that computes the physically relevant solution to the problem. How to determine this good connection. Okay, in red there, I've plotted the set of the saturations where the capillary pressure is continuous. This is the combination of two maximal monotone graphs. So it's a maximal monotone graph from 0, 1 to 0. So it starts from 0, 0, it ends at 1, 1, and it's increasing. In green, I've plotted U, the set of the undercompressive shocks. It's a decreasing curve. So we have two cases, but there's an ending point. We have two cases. The first case, the red curve crosses the green curve. In that case, in fact, the crossing point there, SL and SR, is a steady state for epsilon fixed. For any epsilon, it's a steady state. So it's also a steady state at the limit epsilon tends to 0. Okay, so I got here an undercompressive shock that has to be allowed to do it for the problem. This is the first case. The second case, now, if the two curves do not cross. In fact, in that case, there is no trivial steady state that remains, that is valid for the, in the case epsilon positive, that remains true for epsilon equals 0. That remains a steady state. But you can buy viscosity profile, this stationary here, and that converge towards this point. So you have strong convergence of S pi epsilon towards this value there, yeah, which corresponds to the optimal entropy solution. So let's do now numerical test cases. The capillary pressure I choose are function that depends on S and on LR. So it's a logarithmic function there. So it's exploding near 1. And I have entry what I call entry pressure there that depend on the rock. So in fact, you just shift following the rock type the capillary pressure. I have supposed that Q is equal to 0. So I have pure buoyancy-driven flows. And I have two bell-shaped functions. So FL is in blue and FR is in green. This is the optimal value of the flux at the interface. The first case, I choose PL equals 0, PR equals 0.5. In that case, the set P is in blue then. And the set U here, and they do not intersect. So, at the limit, following the theory I have presented, one should obtain the optimal entropy solution. Now, I change the entry pressure, I choose P is equal to 2. And now, the capillary pressure set is in blue there, it crosses the set U, and then we have a corresponding value of the flux for the flux constraint at the interface. And the solution we should compute is not the optimal entropy solution anymore. Let's test it. Okay. There's an implicit finite volume scheme that I developed during my PhD. I can implement it with an epsilon value. I've said epsilon is equal to 10 to the power minus 3. And I plot the solution. This is x and this is t. So I start with a constant state, 0.5 everywhere. And this is the result of the computation is the following. Okay, I have a slightly smoothed shock that goes from the interface to the left. And when I compute with the optimal entropy solution, I obtain exactly the same. Okay, it's not smooth because there's no diffusion there, and okay, I'm explicit, so it's. But this, okay, for computing this, it takes something like 20 minutes, and this something like 2 seconds. Okay, so that's why it's interesting to compute the vanishing capillary solution, because solving diffusion equation is expensive. Now, the second test case. This is the solution of the degenerate parabolic problem. And in that case, you see that there is 2 waves leaving the interface. So we have really undercompressive shock, a strictly undercompressive shock that is leaving the interface. And when I compute with the constraint Godunov scheme, I obtain the same profile. 2 seconds, 20 minutes. On the same grid. Okay, so let's now compare the convergence speed. So the convergence of S epsilon towards S with respect to epsilon. And okay, so in fact here it's plotted the convergence of S epsilon H, the discrete solution, towards SH on a very fine grid. And what you obtain is that, okay, you obtain something like epsilon, the error behaves like epsilon 1/2. But for the numerical error, it behaves like H. For the, okay, even this is classical, quite classical, it's a first order scheme because it's monotone, it's the Godunov scheme. And my functions I presented are genuinely nonlinear, they're uniformly concave. And then I have a first order error. This is a regularization effect. This, if you choose more complex flux functions that are not uniformly concave, you will lose this accuracy and you will be between, it will be greater than H point 1/2, H power 1/2, but it will be never better than this. Okay, so I have a few minutes to talk about error estimates for this scheme. So we'll see it's not a complete study. It's not completely finished at some point. Okay, there's still open questions. So I'm still in 1D. Okay, my unknowns. Let's plot it. I do a finite volume scheme, which is the same, a finite difference in 1D with uniform grids, it's the same. My edges, I compute xi is equal to a delta x, x a plus 1 is equal to a plus 1 delta x. At this point, I compute fluxes. And in the center of the cells, my cell is there, I have a value there, which is Si plus 1/2. Okay, the values are in the center of the cells, and the edges are. So there's the integer value for edges, and A plus 1/2 is for the cell centers. So I compute this. The flux across the A plus 1's edge is I plus 1 edge is Si plus 1/2 and Si plus 3/2, and I compute the Godunov scheme, and I do the same across the edge I, and I do an explicit scheme. I have explicit values. This is the Godunov flux in the left domain. This is the Godunov flux in the right domain. And this is the Godunov flux at the interface where the constraint has been implemented. First of all, this scheme is monotone. So it means that the derivative of the flux is positive, and with respect to the first variable, and it's negative with respect to the second variable. And also, it's bounded. Here I should have said, okay, it's positive, but it's also bounded. And it's negative, but it's also bounded from here. And under a CFL condition, in fact, one keeps usual CFL condition of type delta t over delta x is bounded. I keep the L infinity bounds that are natural in the problem. Now, let's consider the Riemann problem. Okay. At the cell I, so at the cells across the interface 0. So on the left state, at the left state I have S minus 1/2. On the right state S 1/2. I'm in the interface. So this problem admits traces on the interface, And these traces, I denote them by SL and SR. Okay, so at the interface, I can replace the value SR by the value with the good enough flux at the interface with S1/2 by the good enough flux on the left and the trace. And the same, I put the trace on the interface there. But since it's the okay, let's go to we do some Kruskov-like stuffs, but in a discrete setting. So we want to compare with the kappa, which is bounded between 0 and 1. And thanks to monotonicity, this is the discrete equivalent to sine of a minus k FL of a minus k. But now, this is not possible to write it in the same way because I have a and b. So this, the top there, the t is the maximum value between the both. And this is the minimum value between A and K. And when you do that, the monotonicity of the scheme provides you discrete entropy estimates, like that. And also, at the interface, at the interface, you have also the same, but with the discrete traces that appeared before, that I introduced in the previous slide. So, okay, and because my traces because my traces have been built are exact traces, I can replace the inequality, this discrete entropy contribution flux by the continuous one. This is a trick because we have an inequality that is in a good sense. Okay. And then now we want to we define the piecewise constant in space and time function. The discrete solution SH is constant on the cells and on the time steps. And I have also piecewise constant in time traces on the interface. So I can compute some discrete entropy inequalities in the way of Kruskov, but there I cannot have something. I cannot have 0, because if I had 0 there, I would have an exact entropy solution. So I have something that is negative there, but that we will see, it tends towards 0 when h goes to 0. This means that the scheme is converging. At the limit, you recover the classical, you recover your entropy formulation. Okay. And an important remark is that if my solution is in BV, and okay, this is S and SH, see, if everything is in BV, in fact, this term there is of order 1 in H. In the worst case scenario. Now, what is the exact entropy solution that is here? I can also do this. I have entropy inequalities. I put, instead of kappa, I put L because it's I will change it, and I replaced. It depends now on tau and y instead of x and t. So I double the space variable and I double the time variable. And so in the first equation, in this one, I just replace kappa by the exact solution, but taken y and tau. So it does not depend on x and t. So it's a constant, and I'm allowed to do that. And in this one, where the exact solution depends on tau and y, I put L is a function of x of t. It's a constant. And I integrate. I choose a test function that depends on everybody, and I want to make x close to y and tau close to t. So this is an approximation of the Dirac measure, a smooth approximation of the Dirac measure. And then after some calculations à la Kuznetsov, one obtains that this should be okay. Yes, yt. One obtain this kind of entropy inequalities, but this is once again not the. I think this is xt here. This here it's not 0, but it's a quantity here. C is negative, but I have some weights that appear, and here W also depends on H. So I have some errors that are due to the doubling of variable there. Some are due to the numerical approximation, and some are due to both. This one also depends on H. It's there. Is the difference? Is the time translates of the traces. Okay. So now one can choose H. Epsilon is something fixed. I don't have specified epsilon. It's a free parameter. So I can specify it. I can specify it following so that it's well balanced with H. I can balance H and epsilon. And if I choose, forget this term, okay? If I choose epsilon is equal to H1/2, here I have H1/2, and here H1/2. So I have an error of H1/2, and this should be lower or equal there. No, it's greater or equal, but there should be a minus. Okay. C is negative. Okay. So this is now, if this term, what I can say about this term is that it's I can control it with respect to H and epsilon, and in the worst case scenario, if the traces at the interface are in BV, this is for the epsilon. So I have epsilon, and my error estimate with S1/2 will still hold. If these traces are only in L infinity, in fact I have to choose a different epsilon for H for the time and from the space, and I can balance stuff, and in that case I obtain only H1/3. But in the case where the traces are in BV, I obtain H1/2. But in all this study, the problem is that I need the discrete solution and the solution to be in BV. Is this possible in general? Okay, if this one is not in BV, I can manage. I will obtain 1/6 because I can quantify the numerical diffusion. But this one has to be in BV. Is this true? Sometimes yes, sometimes no. Okay, so let's give a BV estimate to conclude. In the case where FR is equal to FR, it's the same flux function. So it's the case of Colombo and Goati. In that case, my Godunov scheme is just this. Okay. The minimum of the usual Godunov scheme and my constraint. Here's the constraint. I define a modified total variation. What is the modified total variation? It's the total variation away from the interface. But at the interface, I introduce the traces. I compute from S minus 1/2 to the trace, and to S1/2 to the trace. I do not compute the jump across the interface. Okay. But I go until the interface. And the proposition is that if the initial data is BV, this modified total variation quantity is also BV. Is also it stays bounded with time. Okay. So SH is also has also a bounded modified total variation. So and since this total variation is closely related to the usual one, you will get that okay, the function will be BV in a usual sense. Let's see it. How do you prove it? Okay. Now lambda is the set where okay, the constraint is activated. The Godunov flux is greater than the constraint, so you have to constrain the solution. In that case, at the time n. In that case, the traces are the undercompressive, are exactly the undercompressive shock. And you just otherwise, this is one more. Okay. Otherwise, you can choose the trace, which is one value on one side and the other. And if the constraint is not active, in fact, you have the usual total variation and the modified total variation are exactly the same. So now assume that the constraint is not active. Okay. The scheme is the classical Godunov scheme. Then my total variation is just diminishing. The usual result, and my scheme is so-called TVD. If n plus 1, at time s plus 1, the constraint is not active, it's the same. The total variation at time n plus 1 is the usual one, which is smaller than the usual at time n, and which is smaller than which is equal to the modified at time n. So I've got the my modified total variation is diminishing. Now, if the constraint is activated, if I activate the constraint, in fact, the total variation increases. And it increases with this quantity. So I'm not total variation diminishing. That's not possible. But if my constraint is activated at time n, and it stays activated at time n plus 1, in fact, I'm just solving two separate problems, and then I'm TVD in each side, and okay, my total variation is diminishing. But now, if at time n plus 1 the constraint is no more active, I have a change. My new total variation is the smaller than the former one, and another contribution. But this contribution is exactly the opposite of this one. And so you can switch off the constraint at least one more time that you switch it on one more time that you switch it off in the worst case scenario. So I just have this estimate. And from this estimate, one obtains the error estimate for the Godunov scheme. So my time is over, so and thank you.